In today's note, we're going to be looking at measuring distances in space, and as well as looking at some of the planetary models. So we use the astronomical unit, or AU, as one of the measurements to measure distances in space. And again, the reason we use this is that measuring distances in kilometers in space is not practical. And this is because the distance between the objects is so large that it's not practical to use kilometers. An example would be like if I'm trying to measure the distance between two cities, I'm not going to be measuring in centimeters. It's not practical to measure in centimeters because the number is going to be so large. So this is the reason that scientists and astronomers have come up with the astronomical unit. And 1 AU, or astronomical unit, is the average distance between the sun and the earth. That's approximately 150 million kilometers. So 1 AU is going to equal 150 kilometers, 150 million kilometers. So for example, Mercury is 0.39 AU from the sun, and Mars is 1.52 AU from the sun. So again, this makes sense because Mercury, at least in terms of AUs, because Mercury is closer to the sun than Earth, and Mars is farther from the sun than Earth. Another measurement that we use is light years. So as soon as we start to look at distances in our solar system, AUs become impractical. Again, for the same reason that we don't use kilometers, it's because the distance is so large that our AUs would be, the number would be too large. So we use a light year. And the light year is the distance a beam of light can travel in 1 year. So if I were to shine a light, how long or how far would that light be able to travel in a year? And so this is the equivalent, or 1 light year is the equivalent to 63,000 AUs, or 9,000 billion kilometers. So you can try to begin to imagine how far 1 light year actually is, because you wouldn't be able to travel 9,000 billion kilometers in a lifetime. So you can imagine how far 1 light year actually is. So how many light years away? So this is just an example or a look at just in using light years, how far objects are. So in reference to the Earth. So the Earth is approximately 8.3 light minutes from the sun. So that means the light from the sun takes 8.3 minutes to get from the sun when it's emitted to Earth. The Earth is 320 light years from the North Star, or Polaris. So that light again on Polaris, it takes 320 years before that actually hits us. Andromeda, or the Andromeda Galaxy, which is our closest neighboring galaxy, is 2.5 million light years away. We talked about Proxima Centauri, our closest neighboring star, which is 4.3 light years away. From the center of the galaxy, or from Earth to the center of the galaxy, or of the Milky Way, is 26,000 light years. And from the Earth to the oldest galaxy ever found is 13.4 billion light years away, and that's called GNZ11. So again, obviously, we haven't been measuring how long it travels for light for the 13.4 billion years, but we can use computers and calculations to measure and capture light, and we then look at, you can then calculate how far these objects are. This is just a reference of how fast light can travel. So if we were to shine something on Earth, how long would it take to reach the moon? And in real time, it would take 1.255 seconds. So you can see the ball bouncing back and forth. That's how long it would take from light to travel from the Earth to the moon, or the moon to the Earth. And that is covering a distance of 384,400 kilometers. So that's how fast light can travel. Next, we're going to look at the models of planetary motion, or of our solar system. The first is the geocentric model. So this was thought up more than 2,000 years ago, and this was thought, or the idea behind this was that the Earth was the center of the universe. So the Earth was the center, and then everything else that we see in the sky or in space revolves around the Earth, which we can see over to the right here. A small diagram of what that looks like. Next is the heliocentric model, and it's basically a sun-centered model that was revived by Copernicus that you can see below. But basically this idea is that everything revolves around the sun. So this is a little bit more realistic to what our solar system is, in that these objects or the planets rotate around the sun. And there are two key pieces of evidence that support that. First is the orbital radius. So this is that each planet orbits the sun at a different orbital radius. So you can kind of see in the image to your right, each planet is orbiting at a different radius or a different distance. The shorter the orbital radius, the faster a planet moves in its orbit. And secondly, the second piece is the elliptical orbits. So another astronomer, Kepler, noted that the orbits are ellipses, not circles. And then this observation made it easier to predict planetary motions. So once we recognized that they were moving in ellipses, not circles, it's easier to predict their movement. So again, another quick note, we're just looking at the light years and astronomical units, just ways to measure things in space, as well as the geocentric and heliocentric models of planetary motion.